Hi everybody, welcome to another video in Calculus 3, section 13.6, cylinders and quadric surfaces. Right, so this section there's two parts, the cylinders and quadric surface. So the first one is cylinders. The definition of a cylinder is that given a curve C in the plane P and a line L not in P, a cylinder is the surface consisting of all lines parallel to L that's passed through C. So first we will have a curve C, and the curve C is on the plane. So let's say this is the plane that contains in C. So let's say the curve is in that plane, and then we have a line L that is not on the plane P. So we have a plane like this, and then we have a line L. Let's say, oh, this one is L. A cylinder is the collection of all the lines parallel to L that go to C. So just draw a bunch of lines parallel to L and go to C. So it's a cylinder. So of course I can draw that for the whole more than that. So that will trace and give us a cylinder. So when we talk about cylinder, we're not talking about the actual circular cylinder. It is just in this sense. We have the next one here. So first we're going to have a curve C. It could be anything. This time it is a parabola. And this is on the XY plane. So we have a plane and a curve on that plane. Whatever the line L is, it cannot be on the line, cannot be on the plane. So we just have a bunch of parallel lines go through it, and with that we have a cylinder. I mean, this is called a cylinder. In that form. Right. So that's how we define a cylinder. Right. A trace of a surface is the set of all the points at which the surface intersects a plane that is parallel to one of the coordinate planes. Coordinate planes will be x, y, y, z, and z, x. And so we just a trace surface is the point at which the surface. So the surface will intersect a plane that is parallel to one of the coordinate planes. That gives us a trace. So for example, here we have we have a paraboloid here. So that surface. Now on the XY plane, we have the trace of an ellipse or circle here, right? And we call that is the XY trace because that is on the XY plane. And also the trace not only defined on the coordinate planes, we can also define on any plane that parallel to it. So we can draw a plane that is parallel to the XY plane, and in that we can still have a trace on that plane. So any coordinate planes and any plane parallel to it, whatever the intersection with the surface is called a trace. Here we have the YZ trace because that is on the YZ plane. So we draw a YZ plane. We have usually if it is behind the surface, we draw in a dash pattern. The solid will be in front of the surface. So it will be like that. Of course, we can draw any plane that is parallel to the YZ plane here. So in that case, we might have something like like that too. And then same thing for the XZ trace. But usually we just talk about the coordinate planes, meaning X, Y, Y, Z, and ZX. And then from that we can get the idea of what the graph will look like. Right. I sketch the graph of the following cylinders, so we know those are the cylinders. Now, the characteristic of the cylinder and the other graph of the other surfaces is just want to take a look at this equation compared to the bunch of equations that we will study later. What we see is the main difference in the cylinder is that on this equation we do miss one variable. It's missing Z, is missing Y. Right, so that is a big deal. Right, first let's look at x squared plus 4y squared equal to 16. Now let's look on the xy plane. First of all, of course, we identify which one. This one is the x-axis, y-axis here, and z-axis there. X squared plus 4y squared equal to 16. Right, so now we just look at the xy trace. Now usually if we draw the xy trace, I will draw the line parallel to the x-axis on both sides, and then parallel to the y-axis on both sides. So in this case, this is easier to know what trace we're talking about. So this is so parallel to the y-axis, so we're talking about this. Yeah. So if we want to clear here, that probably that doesn't help at all. Anyway, so those are the xy plane. What is this? What does this equation represent? Now, if we divide by 16 on both sides, we have x squared over 16 plus y squared over 4 equal to 1. So why do that? Why do I do that? Actually, we don't even need to do that. But this in next section I will explain why. But for now, if x squared plus 4y squared equal to 16, let's assume that now we focus on the xy trace, which is that plane. If x equal to 0, 4y squared equal to 16, for y squared equal to 16, give us y squared equal to 4, so y equal to plus or minus 2, right? So on the y-axis we have 2, y-intercept 2 and negative 2. Now if y equal to 0, we have x squared equal to 16. So x equal to plus or minus 4. 4 and negative 4. And we connect them, we will have a cylinder. I recommend we draw a pencil first. So I'm sorry, not a cylinder, but an ellipse. So this is xy trace, is an ellipse. This is the curve C we're talking about. Next, this one doesn't have the Z, right? Which means everything on the xy trace of course Z is equal to 0. For xy trace we have Z equal to 0. Now if we change the Z, let's say Z equal to 1, so we move everything up 1 unit. So we just have above that is another ellipse. Or we let Z equal to negative 1, we will have another ellipse below that. Now if we have to draw it, like I said, what in front, what we can see usually is going to be a solid line. Behind that maybe a dashed line. What we see in front, we don't see that on the back. And then when we connect this, in this case exactly we have a cylinder. So that is the cylinder where we have the xz trace. So whatever the missing variable, we're going to draw the trace in the other two variable, and we trace that. Let other variable, let's z change to, let's say, equal to 1. We have let's move 1 unit up, and then z equal to -1, move 1 unit down, and essentially we have a cylinder like that. Right, and if we draw the line, this is going to be the line parallel to L and go through the curve. So that is the cylinder. Right. Next we have x sine z equal to 0. We don't have y. Once again, the cylinder, usually we call the right cylinder, because we can have the cylinder that does not stand upright. It could be like at the slant angle. In that case, there will not be missing any variable. But if the equation missing one variable, it is the right cylinder, meaning that it will be have one thing and then it's straight vertically, or it go up and down, or left and right, but it's going to be the right cylinder. So it will, all the line will be perpendicular to the plane P. So in this case, when I'm talking about the right cylinder, is that the line L is going to be perpendicular to the plane P. Right. Next we have x and z here. So first let's label x and z. So right hand rule here. X and z. So I will draw a line parallel to x. Two line. And two line parallel to z. So that means we're talking about xz plane, and now we study the xz zx trace. So we have the zx trace, meaning that y is equal to 0. Right. X equal to sine z. Let's just make some values. When z equal to 0, z equal to 0, sine of 0 is 0. Z equal to pi over 2, sine of pi over 2 is equal to 1. So let's say pi over 2 is here. X is equal to 1. And then when we have pi, x of sine pi is back to 0. So we have actually going to sine, it's going to be a sine wave. So it's going to be like that. On the xz plane, on the zx plane, on the zx trace, so we have that. And then the y is arbitrary, so we have one curve like this, and then we just move that this plane 1 unit along the y-axis. So we're going to have this. Again, we move everything in the y-axis, so everything will shape in this direction. Let's say shape this much. Everything shape in that direction along the y-axis. and then just keep shifting. Anyway, so we will have a bunch of line like that, and so we have a cylinder. That plane. So it was terrible, but you get the idea. So just like a sine wave, and then it's traced along the y-axis. Not very good graph, but you get the idea. So usually the cylinder is where we have one missing variable. In that case, we have a right cylinder, so in the xz plane, and then we just have. So it looks like this. Kind of. Right, so that is the cylinder. Usually when we have one variable missing, that's the cylinder. Right, quadric surface. So quadric surface described with zero quadric second degree equation in three variables. So we have three variables x, y, and z, and all of this cannot be all zero. If all of this are zero, this is the equation of a plane. We not study about a plane here. Study about surfaces. Right, so in order to graph the surfaces, we'll find the intercepts, the trace, and then try to come up with the graph. Before we do that, let's go for some basic two-dimensional object, namely conics. I mean one-dimensional object in the plane. So let's say we have the equation x squared over a squared plus y squared over b squared equal to 1. So this equation, if we let x equal to 0, y squared move to b squared over y squared equal to b squared, meaning that y equal to b and negative b is the x-intercept, right? If x equal to 0, then y is b or negative b, so that will give us 1. Now if y equal to 0, we have, if y equal to 0, then we have x squared equal to a squared, so x equal to plus or minus 8. And with that we have an ellipse. Right, so just find the intercept, and this is the equation of an ellipse. Next, this is ellipse. Next, let's look at two equations. First, x squared over a squared minus y squared over b squared equal to 1. Now if you let x equal to 0, then y squared equal to negative b squared. That is no solution. So in this case we have no b, no y-intercept, because y squared equal to negative b, there's no solution. If we let y equal to 0, we have x squared equal to a squared, so a is equal to 1. So in this case we do have the x-intercept of a and negative a, but we don't have b, right? But in this case we still graph. Usually when we graph anything involving this equation or its equation, by the way, you should know that this is going to be hyperbola. Usually the way we graph it, because using the intercepts, or in here we say the a squared below x squared, so meaning we go up, I mean left and right a unit, because x is horizontal component, and then b squared below y squared, meaning we go up and down b unit, and we draw the box, and the ellipse will fit inside that box, kind of like this. A squared below x squared, so we'll go negative a, and we'll go negative a and a on the x-axis. Same thing, b squared below y squared, so we'll go b squared, negative b and b on the y-axis, and then just draw a box. that is for ellipse and hyperbola. And then we will draw the diagonal. For hyperbola, we have the diagonal called asymptotes. And then remember, go back to this equation. If x equal to 0, we have no solution. If y equal to 0, we have x equal to negative a and a. So this way, we only have the x intercepts. So we will make a graph. So this is the graph of the hyperbola. Will look like that. Now, if we have something different, for example, if instead of this one, we have y squared over b squared minus x squared over a squared equal to 1. If we left y equal to 0, we have no solution. But if we left x equal to 0, we have plus or minus b. So in this case, we have a parabola that go vertical. So if we start with x squared, horizontal. If we start with y squared, vertical. So those are hyperbola. And then the last one is parabola. I'll just go with the basic. If we have x squared, that is y equal to x squared. Because if we have parabola that open down, so y equal to x squared, look like that, y equal to negative x squared. And then we have x equal to y squared and x equal to negative y squared. So we have parabola that go different direction. So that's the basic. Right. And then we'll go over to the graph of all of this. So ellipsoids, the characteristic here is all the coefficient of a squared, b squared, and c squared, all of them are positive, right? I know I'm talking about the coefficient of x squared, y squared, and z squared. All coefficient of x squared, y squared, and z squared are positive. So coefficient of x squared, y squared, and z squared are positive. In that case, we have an ellipsoid, meaning that when we take two of them, it will be an ellipse. Any two of them will be an ellipse. Therefore, we name it an ellipsoid. So all three traits will be plus. Next, elliptic paraboloid. So notice that when we have that, it is a paraboloid. We have that. That is also a paraboloid. So missing an x squared, y squared. So this is. So in this case, we have z instead of z squared, or x instead of x squared, and y instead of y squared. In that case, we have elliptic paraboloid. So instead of z squared, we have just z. So we're missing a square. We have a single variable instead. So that is elliptic paraboloid. We're going to graph some of it. Hyperboloid one set. So think about this. If we have that is an ellipse. If we have that will be a hyperboloid. If we have that will be a hyperboloid. So I'll try to draw a trace here. So we have two hyperboloid. So we can have two hyperboloid. And then if we don't have z, we're going to have a bunch of ellipse in that sense too. So this is called a hyperboloid one set. Hyperboloid two set, what we see is, so all positive, right? So one negative sign, one set. Two negative sign, two set. meaning that we have the hyperbola will go like this, or that direction. And then we still have a circle. Elliptic cone is where we compare this equation and this equation, because this one have a square, and compare these two. Remember, ellipsoid, hyperboloid, and hyperboloid, we do have the one here. So those are hyperboloids or ellipsoid. When we are missing the one, so we just have all the variables like this. This is elliptic cone. When we have the square, when we don't have the square. And then the hyperbolic, paraboloid, or we sometimes call a shadow, because it looks like a horse shadow, right? So in this case we have, that is a parabola, right? Z equal to x squared, and then z equal to y squared is also a parabola. So of course there will be like that. We just need to practice a lot, but what we see, the summary here is, if we have one or we have a constant in all of those, is either ellipsoid or hyperboloid. All three positive, ellipsoid, one negative, hyperboloid, one set, two negative, hyperboloid of two sets. So we knock out those three equations. Next, we have paraboloid. If we have a variable z instead of z squared, right? Paraboloid, these two, paraboloid. Both of them paraboloid. Both of them positive, elliptic paraboloid. So we have ellipses traced in the paraboloid. If we have a plus and a minus, that gives us a shadow, meaning that we have a parabola open, one of them open like this, and one open down. So one up and down, so kind of like. Probably can draw back a little bit better here. So what I try to draw is, so I draw a whole shadow here. So notice that in one direction the parabola open up, because here like z equal to x squared over a squared, but in the other direction z equal to negative y squared over b squared. This parabola open down. So one parabola open up, one parabola open down. That's why we call this is a shadow. Actually, because it looks like a shadow. Right, so what do we have so far? First, if there's a constant, either ellipsoid or hyperboloid. All positive, ellipsoid, one negative, hyperboloid, one set, two negative, hyperboloids are two sets. Notice that if I write the negative one here, that completely different things. You have to have all the constant to be positive. If we have negative here, multiply everything by negative 1 to turn this to positive. Right, so we knock out those three things. Next, paraboloid is where we have a variable that doesn't raise to a square. And the other two will have the square. So we have a bunch of paraboloid. Here we have paraboloid that both of them. So one open in this direction, the other paraboloid open in this direction, and after that we just have the once again, when we have a variable equal to the other variable square like this, it is paraboloid. So they may both of them turn up, open up. That is in this form elliptic shape. If we have one positive and one negative, so we have one pole open up, one open down, and it looks like a shadow. And the elliptic cone is where we have one variable square equal to the other two. We do not have a constant like the one here. So hopefully that you get some idea. But when all those fail, because we can always just draw the basic. Right, let's sketch this. When we sketch this, just sketch a trace. Let's say if we don't have z, if we don't have y, we don't have x, what do we have? And we just put them all of that together. So let's just say we're going to put the graph here. So what's the graph of this equation? So if we don't have z on the xy plane, so xy trace is where z equal to 0. We have x square over 3 square plus y square equal to 4 square equal to 1. This of course is ellipse. And then we see that on the x-axis it's going to be 3. On the y-axis it's going to be 4. We can draw this. So that is the x, z, x, y trace. For the zx trace, when y equal to 0, x square over 3 square, z square over 2 square equal to 1. This is also ellipse. And then what are we missing? Okay, yz trace, x equal to 0, y square over 4 square plus z square over 2 square equal to 1, also ellipse. So we have all 3 ellipses. In that case we have an egg, or we call the ellipsoid. So notice that we have this also an ellipse, but we have 3 below the axis. So we have 3 on the x-axis, 4 on the y-axis, and 2 on the z-axis. Kind of difficult to draw this. So first, yeah, really difficult to draw this. Yeah, so first we have an ellipse on xy plane. So kind of cut at -3, cut there 4. And then on the z and y, also have an ellipse. So bottom line is we will have an ellipse on the xy plane, and ellipse on the z, and so it is an ellipsoid. Usually it would be better we just draw an ellipsoid like that first. X, y, and z. So that will probably look a lot better than try to fit into the axis. But intercept the x at 3, at y at 4, and z at 2. So that's what we have for an ellipsoid. Next, sketch the surface. This one, we do not have the one here, so this is going to be an ellipsoid because we do not have the square. If we have the square here, that would be a cone, but because we don't, both of them are paraboloid and paraboloid. Both of them are positive, meaning both of them will open up. So this one actually I can try to fit into the axis like this. Right. Let's look at the when z equal to, when x equal to 0 first. So x equal to 0, we have the yz trace. X equal to 0. So this is the parabola that open up. And if we look at y equal to 0, the zx trace y equal to 0, z equal to x squared over 4, that also open up. And then if we look at the xy trace, where y equal to 0, right? When we have this equal to 0, we actually have just one point. Remember, a square is greater than or equal to 0, right? Square greater than or equal to 0. If we have x squared greater than or equal to 0 plus y squared greater than or equal to 0, the only thing that make it equal to 0 is x equal to 0 and y equal to 0. This is the only solution to this equation, because both of them greater than or equal to 0. The only thing that works equal to 0 is when both of them equal to 0. So xy trace is just a point. So now this is actually a little ellipsoid, usually difficult to draw. We would just put the random axis. Usually I just draw the ellipsoid first, then try to fit the axis into it. Now this one we actually can draw. So z equal, on the yz trace we have a parabola. So first we have this one. So parabola. Yeah. And then on the zx trace, we have the parabola as well. And then when xy is traced, we just have a point. Right. So that's good. Now, remember when we try to graph, it is say that sometimes we have to sketch at least 2 traces in parallel planes. So when we have y equal, this is z equal to 0. When we have z equal to 0, we have that. When z equal to 1, if this is equal to 1, we have 1 equal to x squared over 4 plus y squared over 9, which is an ellipse. So when we have z equal to 1, we have a plane z equal to 1, we will have an ellipse. So pretty much, yeah, so this is an ellipsoid like that. Paraboloid. So it's a bunch of, so each side, the side formed by the parabolas, and if we go around, we have concentric ellipse. Right, so that's what it looks like. Or if we're going to draw it without the axis, it will look like this. Yeah, so add a mess. Yeah, so that is the paraboloid. We're not going to draw all of them, just get the idea. Paraboloid one set. Now we have one. If this is one, it is going to be either paraboloid or ellipsoid. So this is going to be hyperboloid because hyperboloid one set because there's one negative sign. Right. So actually we can draw this one relatively well too. Right. And let sum of them equal to 0. Yeah. So once again, when I said we have one here, and I said it ellipsoid or hyperboloid, where we have full x, y, y square and z square. When we have just one without the square, those are paraboloid. So let's say if we have this, that is still a paraboloid because they're missing a square here, even though there's one. But like I said, we just have to recognize and look at different perspective. For example, in the xy trace where z equal to 0, what do we see? That is an ellipse, right? 9 below y square, so 3 up, 3 down. 4 below x square, square root of that, so negative 2 on the left, 2 on the right, and we have an ellipse. That is what happened on the xy plane, an ellipse. I actually can just draw that here. And switch to different colors. Zx trace, y equal to 0. X squared over 4 minus z squared equal to 1. This is, we can write 1 square like this. This is the hyperboloid. 2 under the x, so 2 left, 2 right. Z, 1 up, 1 down. So if we have z on the top and x like this, draw a box and diagonal. This one we have x squared minus z squared. So the hyperbola will open in the x direction. So that's what we have. So open in the x direction. If we look on the xz trace, so let's try to be a little more careful here. Xz trace, right? So let's draw in the xz plane. We have a parabola on the xz plane. Right. Now we let z equal to 0, y equal to 0. Now we let x equal to 0, which will be the yz trace. X equal to 0, y square for 9 minus z square equal to 1. That also a parabola. Open in the y direction. So now if I draw the yz trace, right, right, and then we just link them. So we actually draw without the axis, it would look like this. One ellipse on the top, and then one small ellipse in the middle. So now look like that. So we have ellipse when we cut it horizontal. If we cut that vertical, we will have a parabola. Yeah, so like I said, just find the x-intercept, y-intercept, z-intercept, and then the traces, and we get the idea of what's that look like. Right, just get a lot of practice, and also the ability of draw things in 3D are different from people to people, from person to person. So sometimes you might draw well, and some people draw very well, and some do not. But like I said, when talk about drawing, but the way visualize things, some do better on 3D than the others. But I should be able to see what happened on the two-dimensional plane. Right, let's look at this. What happened on the xy trace? That is when z equal to 0, y square equal to 4x square. What's that? Take the square root on both sides, y equal to plus or minus 2x. Right? So xy plane, I draw parallel to y and parallel to x. And y equal to 2x. So that is just equation of a line. Y equal to 2x and y equal to negative 2x. Right. Next, zx trace. Zx trace when y equal to 0. Z square equal to 4x square. Similarly, that gives us z equal to plus or minus 2x. We take the square root on both sides, that plus or minus. Right, this is only going to be on z and x. So parallel to z. And parallel to x. And once again, we're going to have two line z equal to 2x and z equal to negative 2x. Actually, that is z to negative 2x and z to the 2x. And then sorry, I shouldn't change the color here. And then yz trace where x equal to 0 so this is a point. So what do we see here? And by the way, if x is a constant, we have y squared plus z squared equal to constant, and that is of course an ellipse. So we're going to have an ellipse for certain for every level of x. So think about that. For each x equal to a constant, we have ellipse of constant. So we have an ellipse, and then we have another ellipse. The bigger the value of x, the bigger the ellipse. Well, actually it's not only an ellipse, it is a circle. X y squared plus z squared equal to constant. The smaller x, we have the smaller one, and then same thing on the other side. So what we have is I said sometimes it's better to draw the graph first. So remember, we have a bunch of circle but along the x-axis. So let's say if I put the x-axis like this, say that is the x-axis, go this way, 0 is here. The bigger the x-axis, the bigger the radius. So kind of we have a cone here, and parallel to the x-axis we're going to have a bunch of ellipses. In this case it is circle. So that's just like a double cone, if you will. Yeah, it's kind of difficult. But once again, the reason we see the graph like this is when x equal to constant, we have an ellipse. So we have a bunch of ellipses. Bigger the x, the bigger the ellipse. Smaller the x, smaller the ellipse. So we have a double cone. See if I can draw this better. Just draw horizontal. So this is the x-axis, y-axis, and z-axis. Yeah, that look better. We have a double cone line along the x-axis. Right. The reason that we know the cone aligned along the x-axis because when x is constant, we have an ellipse. Because if we have, let's say, the equation is x squared plus y squared equal to z squared, this is going to be a cone aligned on the z-axis. Yeah, so that is the case. When z equal to constant, we have an ellipse or a circle. So whatever square stand by itself is we have a cone aligned on that axis. Right. So here is just an example. Like I said, when we encounter a problem, I will just draw a bunch of traces and see the graph of it. It might be difficult to visualize things on 3D. But other than that, this is what we have for the surfaces in three-dimensional space. Don't worry about it. Like I said, none of this is calculus. When we get to the next chapter, we start getting calculus, and it could be nice if we can graph this. Of course, when we can graph, we can explain all the things. But sometimes the calculus, the math from the equation, like I said, when we do a bunch of examples, we should be able to get used to the graph. But if you see the online, there's the on eCampus, there's the button that says the formula for final exam. They have this chart on it, so at least that. So if you practice and then you still, and I should say just if you practice enough, then you should get the idea of what the graph will look like. But the way to do that is just look at different traces and then x and y intercept, and then try to put all together in three-dimensional space. Right. When we get to a particular problem later, we'll get back to this. But for now, I'm just gonna stop this section here. Later on, if we have to do a problem where we need to draw, I'm going to do each one of them again. Right. So stop this section here and see you in another video in Calculus 3. As always, thank you for watching.